Good morning, good afternoon, and good evening, everyone, on this very, very hot Wednesday afternoon. My name is Samia Jalay-Sheikh, and I'm a member of the SaRS webinar committee. It is my great pleasure today to chair the webinar on behalf of SaRS, and I would like to take this opportunity to welcome everyone in joining us today from across the globe. Today's webinar is part 4 of a 5-part series on the basics of functional safety. This series is presented by Engineering Safety Consultants, ESC. The topic today is Software Safety Considerations to IEC 61508-3. It's presented by Dr. Fan Yi. So if I go over the programme for today, so following the introduction, Dr. Yi is going to do his presentation for 45 minutes, approximately 45 minutes, after which there will be a Q&A session. If for the Q&A session, you can make use of the chat box function, after which I'll be able to give you information about upcoming webinars and how to access this webinar in the members area. And finally, there will be a feedback form where we'd really appreciate it if you could complete the feedback form. Just to let everyone know, this webinar is being recorded. Before we go any further, very quickly give you a quick brief on how to use Click Meeting. So we have got this AV pod here. If it's getting in the way of your viewing area, you can move it around to where you think is suitable, or you can use this little icon on the bottom right hand corner to dock the AV pod on the right hand side of the screen. You can use these buttons here to either expand the chat area or the screen, or reduce, or whichever way you please. And then finally, there is this little question mark, this little speech bubble with a question mark in it. When writing a question, if you can click that first, then we can identify any questions that are being raised by the audience today. Oh, and one final thing is that when you go to exit the event, if you can exit it via the event board. Okay, so our guest speaker today is Dr. Fan Yi. He's a principal consultant at ESC. He has 16 years experience on functional safety. He's also a committee member for IEC 61508-3 and IEC 62443. Dr. Fan Yi has taught courses on safety-related software, ICS Cyber Security. He has chaired safety study workshops, including PHAs, HAZOPs and LOPAs, as well as chairing workshops. He's also led safety studies, including QRAs, FMEAs, and SIL assessments, just to name a few. If I can kindly request that Dr. Fan Yi turn his camera and mic on, and I'll hand over to you now.
Okay, thank you. Right. Okay, welcome to this fourth installment of the 5 webinar series on the basics of functional safety. So in this webinar, we're going to talk about software safety. So previously, if you have attended the previous sessions, you have been introduced to the concept of functional safety management systems, and the HAZOPs and LOPAs and their pitfalls, and also on different methods to determine the safety integrity levels, the SIL determination methods. In this webinar, what we're talking about is quite different from what you have been hearing on those functional safety aspects, mostly focusing on initial hazard identification, risk assessment, and focusing on SIL determination, probably SIL verification as well, focusing on calculations of random hardware failures, etc., etc. But this time we're looking at software safety, and software safety is quite different from those random hardware aspects we'll be looking at. So in this webinar, we're going to look at those 4 different topics. And so firstly, we'll look at software. So what do we mean by software, and how does software relate to functional safety? And then we'll move on to different software safety standards, how those different safety standards address software safety. And then we drill down to IEC 61508, which is the basic functional safety standards, and part 3 specifically dealing with software aspect of safety-related system. And then followed by the final topic, focusing on how do we achieve compliance with IEC 61508, part 3 on software safety. So first, what do we mean by software and software safety? So here is the definition given by these standards in 61508, part 4. Software is the intellectual creation comprising the programs, procedures, data, rules, and any associated documentation pertaining to the operating of a data processing system. So it's not just a program, we install on our computers, an app we install on our phone. So it comprises the program itself, as well as all those supporting elements associated with operating that a data processing system. And traditionally, in IT words, we would have 2 major camps. We got Windows and Mac operating system. On top of those, you have lots of different applications that run on these different camps. Of course, we have Linux as well. Mac and Linux, the both sort of Unix camp. So again, still 2 major camps. Nowadays we have Android on our tablets and our phones as well. So move on to different software types. So we're talking about the standard differentiates the system software and application software. It has important implication in terms of compliance with the standards. So system software, we're talking about the ones that provide a platform for the application software to run on top of it. So in the IT domain, on the left-hand side of the diagram, you'll see the operating system. We have 3 major operating systems: the Windows operating system, the Apple operating system, and the Linux operating systems. Those are the system software. So they provide operating system device drivers, language processors, and utilities that come with the operating system once you install it on your computer. And those are the system software. They provide platform for a application software to run on top of it. In terms of the operating application software, you have the ones for productivity, for example, Microsoft Offices, games and social medias, and all the other tools, etc., etc. On the OT side, so talking about operational technology, on the right-hand side, the diagram shows, at the bottom, we have the PLC embedded software. So the programmable logic controllers, there are a handful of major players on the market, like Siemens and ABBs. You buy their PLCs, they come up with the embedded software already installed on it. So the operating system already loaded onto those devices. And those are generic ones, just like our operating system in IT is generic. You can run any number of application software on top of it. And on the application software side, for the OT domain, we would have industry and application-specific logics, application logics run on top of those generic PLCs. So it can run, our power plant, our trains, our shipping, offshore, onshore machinery, so you name it. All those industry control systems can run on those generic PLCs. So that's the distinction between system software and application software. Now comes to the software, we also need to distinguish, the type of failures we're dealing with. So for hardware, we always have both random hardware failure, we also have systematic failures. So there are 2 types of failures, random failure and systematic failure. But when we refer to random failures, we always put hardware, the term hardware in it. It's because random failure only associated with hardware. So a failure occurring at a random time, which results from one or more of the possible degradation mechanism in the hardware. For example, corrosion, thermal stressing, wear out, etc., etc. So those are all associated with random. On the other hand, the software, they don't fail randomly. So that's all the software failures are systematic. So systematic failures referring to the failure related to, in a deterministic way, to certain causes, which can only be eliminated by a modification of the design or the manufacturing process, operational procedures, documentation, or other relevant factors. Example, systematic failures, causes for systematic failures include, requirement specification, the faults in the requirement specification, in the design, in the implementation of the software, so the source code, in the design, manufacture, installation, or operation of the hardware. So hardware have both random failures and systematic failures, but for software, all failures are systematic. You have to go back into the source to remove it, to eliminate the failures, causes of the failures. If it is requirements faults, if it is source code error, you have to go back in and correct those and recompile and reinstall, recommission system, so to remove those faults and failures. So from a software perspective, the failure modes include crash, incorrect values, incorrect outputs being generated, or timing errors. So the software could crash. We all have experience of blue screen of death in Windows, on our Mac computers, incorrect output being generated by the software, or the timing errors, results being generated too early, too late, then those are, or coming out of wrong sequence order. There are different defect types too, functional or intrinsic. So the functional is, the application logic being implemented incorrectly. Intrinsic, the ones to do with the software development environment, so they can be identified regardless of what software is intended to do. For example, divide by 0. So if you have your denominator have a 0 in its value, that would always be identified. If you go your integer or numeric overflow or string overflow, or your so all of those can be readily identified through static analysis or dynamic analysis. Those are intrinsic. They are not related to the function you're trying to implement. So that's the distinction between hardware and software, and a gentle introduction on the software failure, the nature of the software failure. They are systematic in nature. Now, we always heard the term safety critical software. What do we mean by safety critical software? Failure or malfunction of the system or the software that could give rise to or contribute to a fatal accident. That would be termed as safety critical software. From a standard perspective, they use the term safety related software. So any software that is being part of a safety related function or safety related system, it would be considered safety related software. Now, because in the industry we're working on high risk industries, we could experience failures of the system that lead to catastrophic accidents, including the ones shown on the diagrams. So we have Deepwater Horizon, we have rail car derailment, which contain hazardous chemicals. We have mid-air collisions. We have bounce field fire and explosion. We have a Paparaffa type of accidents that happened in the past. Although none of these are specifically attributed to software faults leading to the failure and accidents. However, software failures, software faults can and indeed have contributed to a few well-known incidents in the past that's published and studied in literature. Let's take a few examples of those. So first one, so we'll look at the Airbus. So it's a military A400M military transport aircraft that it was crashed in 2015 during its pre-delivery test flight in Spain. That led to 4 fatalities, so the 4 people on board performing the test. The cause that, following investigation, suggests it was a critical part of the configuration data got accidentally wiped during the installation process. That led to 3 of the 4 engines failure when the aircraft was airborne. Of course, it can't fly with just 1 engine left, leading to the crash. So the piece of important information that got wiped was the file that store in the torque calibration parameters, which is critical to the flight. And so that is you can't see that as a configuration management failure, but again, it suggests, it's part of the software that's been missing or been, deleted during the installation process. The next example has been widely studied in the literature and often used to highlight the danger of software reuse. So the accident related to Ariane 5 spacecraft that was, happened on 4th of June 1996. It was developed by European Space Agency, spent 10 years, $7 billion for the development. The Ariane 5, after launch, just 40 or so seconds, it self-destruct. The root cause for that accident was that the piece of reused software was previously used successfully in Ariane 4. It's actually used before launch to align the inertial reference system. So it has no role to play after the spacecraft is launched. So if the software was stopped executing following the launch, it would not cause the problem. It turned out that in the original code, it has a converting error. The data conversion from a 64-bit floating point to a 16-bit signed integer type. It happens, using the high-level languages. If you're familiar with C programming language, you can cast one data type to another data type. And that, of course, 64-bit floating point can hold a much larger number in comparison with 16-bit signed integer, and that caused the data overflow. So it can't hold that big number, and overflow got truncated, and the number will be wildly different from the original number. That led to the guidance system shutdown. And that then, of course, it passed to control to an identical redundant unit, but it failed in the same manner a few milliseconds before the main control. So redundancy doesn't help dealing with systematic software failures. You're running the same software. If it fails on one unit, it will fail on the redundant unit the same way. So that, again, that highlighted the danger of software reuse. Even though you previously used them successfully, it doesn't mean that when you reuse it, it would run successfully again in the new hardware. It's likely that in the Ariane 5 stage, the hardware, the processor power is much more advanced, and the generated data is a lot more. In the Ariane 4 stage, the number was much smaller, which the conversion didn't cause an overflow. Now, this accident's also quite interesting. Another factor that, another type of software failure that you'd experience when the system has been running for a long period of time, so latent software failure. So this involved in the Patriot missile failure, happened in the first Gulf War in 1991. It failed to intercept. It's the missile interception system. So it calculates the trajectory of the incoming missile and launch a missile to counter it and destroy the incoming attacking missile. So it failed to intercept an incoming Iraqi Scud missile and caused 28 soldiers being killed and 100 more being injured. This was to do with a software running error. So incorrectly calculate the time. The clock cycles, the system maintains its own clock time. So it has the clock cycle of 1/10 of a second was represented as a 24-bit fixed point type in the software. That itself is in preset, contains a very small error. Actually, so the error is 9.5 times 10 to the power minus 8 seconds. So 1/10 of a second, every 1/10 of a second, it gives 1.5 times 10 to the minus 8 seconds. It's very, very small. However, at the time of the incident, the system was up for about 100 hours now. And the inaccuracy was actually built up to about 1/3 of a second. And of course, 1/3 of a second is very significant for the missile. It can fly for a long distance in that time period. And the calculation is in that bracket. You can see how it was calculated to 100 hours lead to of 1/3 of a second inaccuracy. That caused the system to react too late to the incoming missile and leading to the accident. So, we all experience with our Windows operating system or laptop running for a long period of time, then the system becomes sluggish. Sometimes it just, crashes due to, software design bugs in the software. Sometimes the allocated memory failed to release it after use. And then over time, the system resources got depleted and you experience a crash. Another example, more recent ones we had is a Boeing 737 MAX. That will two accidents happened. One in 2018 in Indonesia that caused 189 deaths. The other one about 6 months later in 2019 in Ethiopia, leading to 157 deaths. In total of about 350 people got killed in those two separate accidents, and that led to the whole fleet being grounded for quite some time. They're still in the process of getting them back on to be approved to back fly again. So it's attributed to, this is one of the first accidents actually attributed to software. For lots of flight accidents, and they blame, many of those cases blame, human error, the pilots miss or not handling system appropriately. In this case, this is a first instance, the accident that's actually attributed to the software. So it's the MCAS, Neuron Characteristic Augmentation System. Because they have, this model has a bigger engine, they were mounted further forward. And in order to counter the potential stalling, they have to pitch the plane's nose down. So the software system, the MCAS, is to pitch the plane's nose down when they detect a potential stalling condition. In this case, so the software analysis for this this module was considered as a critical level C. So DO178C, later we introduce this standards. Because it's categorized as critical level C, there's no need to make use of redundant sensors, hardware sensors. So that gives a single point of failure. Although the flats, they all equipped with multiple sensors, actually at least two redundant sensors. They only use one. They only need to use one because they felt the criticality level is not that high. So C, you see the highest is A, so A, B, C, and D, E. Later on, we'll see. This was a failure of the requirements engineering. So they didn't expect that there is a potential repeated activation for MACS, even though one activation won't do much, the trimming the nose down by a small degree. But in this, in both cases, the sensor, the hardware sensor, is actually prone to failure. The sensor failed, leading to the software have to repeatedly apply because they have the rating that's saying the plane is stalling. Repeatedly apply nose down. Eventually, making both airplane actually just crashing down to the ground, with a very hard angle. That's the cause of the accidents. So we've seen those different examples of software failure that can lead to fatal accidents, and there are more. You will see more in the future, because the software plays more important role, or more and more functionalities being implemented in software, and more software getting more and more complex. So we'll expect more of those coming up in the future as well. And there's added dimension to the software, and leading to safety accidents, because there's this security dimensions, the cybersecurity, cyber attack on this critical software that could lead to a similar effect of system failure and resulting accidents. So you can see those day in, day out, the news paper on the software running our cars, running our plane, running our NHS healthcare system. They could all failure of the software, either due to faults being introduced in the software, or due to cyber attack. They can lead to similar accidents we have seen. Now move on to introducing the software safety standards. So there are a few safety standards dealing with the topic of software safety, and they are often being viewed by the regulator as benchmark. So regulator actually use it as a benchmark to assess whether you're comply with the standards, then assess whether you comply with the legislation and the law. So 61508, IEC 61508 is a basic functional safety standards. It's being used to develop, as a basis to develop a sector-specific standards. So it plays a key role in all IEC series of standards. It has 8 parts. The part 0 is just talking about functional safety and IEC 61508, the relationship between functional safety and 61508. Part 1 is general requirements. Part 2 talking about system hardware requirements. Part 3 focusing on software requirements. Part 4 give the definitions of the terms used. So those 4, so part 1, 2, 3, 4, mainly the normative requirements, the mandatory requirements are contained in those parts. Part 5, 6, and 7, they are containing informative parts. Part 5 talking about different seal determination methods. In the previous seminar of the series, we're talking about seal determination methods, guidance on full application of part 2 and part 3. So that is in part 6. Overview of the Technis measures in part 7. So basically, in the mandatory requirements part 2 and part 3, each have a number of tables with different techniques and measures to deal with systematic faults in different stages of a safety lifecycle, in the design development lifecycle. Each of those techniques and measures are given an overview in part 7 if you want to find out more information about it. Emphasis on the systematic lifecycle approach, safety lifecycle approach, in the diagram showing, starting from concept, specification, to design, implementation, operation, maintenance, modification, decommissioning. So that's the essence of it. Because it's a basic functional safety standards, all the principles that been brought up in that standard are being implemented in sector-specific standards. One of those is the IEC 61511, the process sector-specific functional safety standards. I forgot to mention that 61508, the current edition, the edition 2, released in 2010, but we're actively working on the edition 3. It should come out in the next 2 or 3 years. And the standards, we've been working on it for a few years now. But the standard does have a long life cycle in implementing and coming out. So we'll have more guidance on cybersecurity, on the use of artificial intelligence, molecule processing, Internet of Things, etc., all those current trending technology being used in the industry. Now 61511 is the process sector specific standards. They have 3 parts, focusing. The part 1 is the normative requirements, focusing on the framework, definition, system, hardware and software requirements. Part 2 gives the guidance on part 1. And part 3 give a guidance on seal determination, again, because seal determination is such an important element when you get it wrong, you won't have adequate protection of your system, or if you get it too high, it then place too much a burden on implementing and maintaining such a system. Current edition is edition 2, and released in 2016. Now, in the Rails industry, we have EN 50128, which is focused on the software aspect. They have separate standards for system, for hardware and communication systems. So EN 50126 in the overall system, 50129 covers the hardware, 50128 covers the software, and 50159 covers the communication systems. Now, in the civil aviation, I mentioned the DO178. So the title is Software Constellation, Airborne Systems, and Equipment Certification. The current edition is DO178C, released in 2011. The software were given, different criticality levels, A to E, based on the failure consequences, because they're only dealing with the software, so they're not talking about frequency, the probability. So they only focus on the consequences. If you recall from the previous webinars on SIL determination, mostly in the process sector, you would have to, the risk is, combination of frequency and consequences. But since we're only dealing with the software, so DO178C, just looking at the criticality level. If a failure that could lead to a mid-air collision, that would likely to be classified as category level A. If it is an onboard entertainment system, that probably is categorized as category E. Now, in the defense sector, we have in the UK DEFSTAN, they have 0055. The title is Requirements for Safety of Programmable Elements in Defense Systems. So issue 2 was published in 1997 and withdrawn in 2007 in favor of civil standards. Somehow at a later stage it was resurrected. In 2016, it was the issue 4 was published. I think that's the current edition. So it still provide guidance on adoption of civil standards. So there is a desire to adopt the civil standards as much as possible. Of course, we're talking about defense delta. So some specific defense requirements you have to address as well. So they give in their annexes, they give guidance on how to adopt civil standards such as the IEC 61508 for general functional safety software. If it is in the aviation sector, they encourage you to use DO178C standard. So that's sort of a summary of those standards. And when we come back to IEC 61508, as I mentioned, is a generic basic functional safety standards. It has been used to develop sector-specific standards, including in the machinery 62061, in the process sector 61511, in the nuclear 61513, power drive, and the railway application. Therefore, if you understand or fully appreciate the requirements of 61508, you will have little difficulty in navigating or applying those in the sector-specific standards. And also, these 61508 can be used standalone by device manufacturers. So they can engineer their piece of device to be used in functional safety or different domains and certified to meet certain SIL requirements, and then they can market it as such. And for those devices that are SIL certified on the market, you can take them and directly use to meet the sector-specific standard. So that's the advantage. And there is a large number of those devices available on the market. So that's sort of summarizing the standards that cover software safety in the high-risk industry. Now we'll move on to 61508 Part 3, which is the software part on the functional safety from the IEC 61508. It has to be read in conjunction with part 1 and part 2. So part 1 provides the overall general requirements. Part 2 provide requirements on the hardware and system. They are interlinked. So the scope of the part 3 is within the context of part 1 and part 2. And the prerequisite for moving into applying the requirements of the part 3 is that you have the EEP safety requirement specification. That is, coming from your the earlier hazard identification risk assessment. So EEP stands for electrical programmable electronic safety requirement specification. They cover all software forming the product or used in the process of developing the product, including new, modified, or reused software. So that covers the operating and system software, covers communication software, covers human computer interface functions, and development supporting tools, firmware, and application software. So all software elements that is forming part of a safety-related system is within the scope of part 3. Now, the main clauses, the main contents, you'll see, if you're familiar with the standard, you'll see part 1, part 2, part 3, they have a similar structure. So they have all those 8 clauses with forward and the introduction. Part 3, they don't repeating the ones that stroked out is basically they have the same content as part 1, scope, normative requirements, references, definition of abbreviations are all just cross-reference to part 4 because that part is dedicated to the definitions and abbreviations and conformance requirements. The real requirements that left in the part 3 is the clause 6 and clause 7. Clause 6 is just having a bit of additional requirements in addition from those that are already listed in part 1. As you can probably imagine, it's covering the configuration management requirements because software configuration management is a key to software-related projects. If you got the configuration, the baseline wrong, you could have introduced the incidents and accidents in the finished system. That's not the ones you're verified and validated to be run on the finished system. So the key requirements remain part 7, talking about software safety lifecycle requirements, and break it down into the different stages of software development lifecycle. We'll come to those later on. They have a number of annexes, 7 of them. Most of them are informative, providing information. Annex A and D, they are normative. When we say normative, they are mandatory requirements. So Annex A guides to the selection of techniques and measures. As I mentioned, both Part 2 and Part 3 have a number of tables detailing different techniques and measures to help you avoid introducing systematic faults into the design development of the system, or techniques and measures to help you detect faults and errors that are introduced in the system. A contains the high-level tables. Some of the items in those tables could then expand into a number of detailed tables. For example, when we talk about a static analysis technique, static analysis is a group of techniques, so you would have a detailed tables in Annex B. The Annex D is that you have to produce a software manual for compliant items. Basically, you're selling the product in the functional safety domain, you need to have a proper manual to tell the end user how to use it safely. So we talked about earlier, the certified product can be used in sector-specific implementation, and the end user or the system integrator needs to know how to use it safely, and what are the caveats, what are the known issues that you need to be known about. In the main requirements, so you would see a note, have the similar text for different appearing in clause 7, different subclauses in clause 7. So for the selection of appropriate techniques and measures to implement the requirements of this clause, the following properties should be considered. So, of course, in different stages, you have different properties to be considered. In the requirement stage, ambiguity of the requirements, ambiguity, completeness of the requirements. In the design stage, you have different properties. So different properties, then they have guidance, in Annex C, talking about, based on the properties, which alternative techniques and measures would work better to achieve your desired properties of those application. So the main safety requirements in clause 7, they have the note always stating, in terms of selecting of appropriate techniques and measures, this you need to go to Annex A and Annex B for those. So they appear in clause 7.22, 7.4, 7.5, 7, 8, and 9, and even in clause 8 on functional safety assessment. The Technis measures, you see, they are formatted in terms of tables. So for each of those items, for different seal level, so seal 1, seal 2, seal 3, seal 4, you may be familiar with those terms. They have designation for those techniques. There is highly recommended, they have the full designations. Highly recommended, recommended, and no recommendations, or not recommended. So if it is highly recommended, if you're not using that for your specific application, for that seal level, you have to provide a strong justification why you're not using it, and agree with your functional safety assessor. If it is recommended, and if you're not using it, again, you need to provide justification why you're not using it, but with a less rigor in terms of the comparison with highly recommended techniques and measures. No recommendations, or they just techniques that you can either use it or not using it, and there's no issue from the standard perspective. There are a few of those techniques and measures that are actually positively not recommended. So if you are using it, you have to provide a strong justification why you're using it and how you guard against those potential issues by using it. For example, dynamic memory allocation. For example, using artificial intelligence. It's not recommended for higher seal levels. So when you use it, you have to provide a justification why you think that you can make sure the system is still safe. Now, in terms of the requirements, the summary of the requirements, we say the requirements are mainly contained in clause 7, and clause 6 have some additional requirements. Clause 8, functional safety assessment, is the same requirements as in part 1. The main requirements are in clause 7. They cover in different software development life cycle. Life cycles, break it down into requirement specification, into design implementation, into the software and hardware integration, software validation, planning and validation, modification, operation modification, and software modification, and verification is separated out as a separate stage. So within the design development, again, you have the requirements, architectural design, language and tool selection, detailed design, coding, module tests, and software integrations. All of those, if you are, experienced or familiar with the software engineering process, it's a systematic process. For each of those processes, there are requirements being specified in the standards. Now, going to the last module of this webinar, we're talking about how do we, establish or demonstrate compliance with requirements as per 61508. As I said earlier, actually, it's generic, it's basic functional safety standards. The requirements from 61508, you'll find that they're very much similar requirements from the other industry standards in other domains, such as the rail industry, even EN 50108. You found very much similar requirements. And even DO 178C, you will find, there are many similarities, because from a software design perspective, you need to just apply a rigorous process and employ competent people, have rigorous V&V process, verification validation process in place to make sure that we're not introducing any systematic faults into the system. So we talked about safety life cycles. So 61508, they have this overall safety life cycle starting from your concept and high-level hazard and risk assessment. That's when you determine your SIL level, and flowing from there, you establish the high-level, the overall safety requirements. That's your EEP safety requirements, and those safety requirements then come down to the stages where stage 10 is where you actually realize that system. So basically you implement that system. So this realization stage is the key focus, and where we then branch it out into the hardware implementation, software implementation. On the top left diagram, you can see. And the software implementation then have its own software safety lifecycle, which is documented in the part 3 of the standard. So when we zoom in, looking at the box 10 on that activity safety-related system realization, we say you have separate system safety lifecycle focusing on hardware and a separate software safety lifecycle focuses on the software. So left-hand side is hardware, and then right-hand side is the software. They are closely interrelated. So your software team and the hardware team will have to closely work together to achieve, to realize the safety-related requirements of box 10. Once they are successfully validated and integrated, you move on to box 12 to the next stage of overall installation and commissioning. So when we're looking at even closer in part 3, the relationship between software scope and hardware scope, that's the diagram. On the software scope, we're starting from the EEP system design requirements. We derive our software safety requirements, move on to the software design development, then we integrate that onto the hardware system to achieve the final finished product or integrated safety-related system. In the standards, it's listed or it described or used the V model, design development model, as a reference model to describe all those key requirements and concepts in the standards in the part 3. However, this V model is not a mandatory model. It's not saying that in order to comply with 61508, you have to use the V model for your software system design development. That's not the case. It's an optional model, and it's just it lends it so well in elaborating those detailed requirements from a software perspective. It breaks down into those nice distinguishable stages, and it also highlights the verification and validation activities. So those dashed lines with the arrows, there are verification activities. On the left-hand side of the model, is almost like a waterfall model, going from requirement specification to the architectural design, to system design, module design, and to coding and implementation. On the right-hand side of the diagram, then you have the module testing. Those are verification steps, integration testing, and then integration onto the target hardware, and then validate the complete system. So it's just a nice model to illustrate those ideas. So it doesn't preclude many other lifecycle activities or lifecycle models. For example, now in the agile model, we'll talk about a bit later, it's very popular in industry. And there are a few caveats if you apply the agile model to safety-related system design development. Now, so when we talk about the software design development models, the first one, first systematic model was the waterfall model. So you go from one stage to the other. They're all distinguishable stages. You have to complete all the activities in the one stage before you move on to the next stage. So you requirements definition, you finish all the requirements definition, validated that the requirements specified met the objective of that stage before you move on to the system and software design, and you validate, verify that is accurate or complete all the tasks and all the activities are complete before you move on to implementing unit testing and so on and so on. So that's the oldest software design development model. It still plays an important role in the modern software design development, especially related to safety-related systems. As long as you have a clear and complete safety requirements from the beginning, and you expect that the requirements won't change much throughout the design development stage. Sometimes, complex systems have a long life cycle in the design development, take years to finish. Often, requirements creeps, the requirements will change. It makes all your efforts, you have to revisit, and you go back to revisit earlier stages to work on the waterfall model. So it's not quite working well with a large complex system that takes years to finish. Also doesn't work well with commercial system design development, because the requirements just changing, so its requirements are dynamic, it's changed so frequently. It doesn't deal well with changing requirements. But for safety-related system, often the safety requirements is fairly stable, won't change much, well established at the very beginning, then waterfall model is still a sound model to use. Then there's refinement in incremental design development, so more of an iterative process. So you have your requirements established, you allocate your requirements to increments. So you if it is a complex system, you divide them into divide them into smaller chunks. Maybe you focus on critical modules first, the key core functionalities first. So you have those as a separate increment. You start from those. And then, when you finish that increment, you integrate onto the existing, the partially complete system, until you then move on to the next increment. And make sure that each increment doesn't break previously working system. So that is the often called incremental development or iterative development process that works well with the sort of requirements changing. You can work with the core requirements, more stable requirements first. And once you get a prototype or working system, even though it's not complete, you can go to the client and actually show them how it works, and then elicit or refine your requirements further for the subsequent design development. So that's that. Then there's coming this agile model, which is very popular at the moment. It's really nothing fancy. It's a different word for incremental development, iterative development. You just go with, but the agile model focuses on talking about very quick iterations. So each iteration, you implement some of the requirements until you get the finished product. You integrate, and within each cycle, you go through those distinctive phases. Requirements, architecture design, detailed design, coding, and once you're done, V&V integrate with the working system until you get your system finished. And it's quite common, it's quite more popular in the current industry software design development software systems design development. It's that many systems, actually the open-ended, those commercial software, they have no end date. You just add more features. There are often more features as a requirement once the software is been released for use. They move on to the next iteration, adding more features to it. We'll look at their manifesto. They focusing on individual interactions over process and tools. They're focusing on working software over comprehensive documentation. They focus on responding to change over following a plan. So those are all good. As a software engineer, we all of us wanted to see the actual software working. We wanted to run it and then put it on the system, and it actually runs. It's all good. However, that all of those principles actually run against the requirements of the standards. from a functional safety perspective, there's a focus, the standards have a focus on the process and tools. There's a focus on comprehensive documentation. That's how you demonstrate you comply with the standards. You demonstrate to your regulators, you demonstrate, functional safety is not just, I've done this. You have to demonstrate that you have done it. You need to be seen to have achieved functional safety. Responding to change and following a plan, we're actually in functional safety, we are very much focused on you have to have a plan. You go through the systematic safety life cycle in order to go through all those different life cycle stages to achieve compliance with the standards. In those process, you make sure you have comprehensive documentation to demonstrate as an evidence to demonstrate you comply with the standards. You need to have a very good process and tools. So those manifestos, those principles, if you don't make any changes to the agile process, you won't be able to use in the functional safety system design development. But if you are open to adapt, to actually embrace, we focus on both sides, and we also adapt that agile process. We in each of those quick iterations make sure you still get documentation, make sure you're still following your plan set out at the very beginning, make sure you still focus, follow your established process and tools, that you're not cutting corners. And then you're fine. There are even books written by the committee member that's on how to apply an agile process to implement a safety-related system that meet the standard 61508. So our mission as a safety engineer in safety-related software development, to build the right software and to build the software right. So they have two different meanings. So building the right software means that the software is meeting the intended requirements of the clients, and also the safety requirements, not just the clients. We have to make sure it's safe. So the end product is safe. Build the software right is by following a systematic process. So meet the safety, the end results, we're trying to meet the functional safety requirements. We're also trying to meet the safety integrity requirements. That requires the requirements are specified correctly. You may be surprised that lots of issues related to the delivered software is actually can be attributed to the software, the requirements. The requirements are not specified correctly. Omission, commission, or conflicting requirements, about 40%, even more. So final software meet the specified requirements. End-to-end verification is called validation. From requirements to final realization, we need to have a systematic process, software lifecycle, to reduce the defect density in the delivered safety-related software to an acceptable level. And there are techniques and measures available documented in the standards to encourage you to apply and to achieve those. Defects include those in the requirements, as I said. Requirements defects account for quite a large percentage. Verification in each lifecycle phase to ensure the software is built right. Now, this, from the standard perspective, in terms of compliance, we need to have insurance and assurance. So insurance covers the, you need to have, you're doing it right. You have a robust process. You have capable people. You have best practice. You employ best practice technology. Assurance, including the V&V activities, safety audit, functional safety assessment, certification. The regulator may come in and the regulating process. They are assurance, part of their assurance. So that's sort of conclude this webinar, basically a light introduction to the topic of functional safety from a software perspective. And in terms of the resources, the standards, of course, reading and understanding the standards is important. So safety standards 61508 part 3 for software, and sector-specific standards 61511, 50128, DO178C, DEF stand 0056, and there are other standards as well. And from our perspective, we deliver lots of training courses on the function safety from, of course, the system perspective and also from software perspective. And we also offer consultancy to acting as a functional safety assessor. So functional safety assessment assessors, FSA. So that is often the mandatory requirements from a standard perspective. So you need to have, especially with a higher SEAL level, SEAL 2, SEAL 3, SEAL 4, you often need to employ independent FSA assessor for your project. Make sure that you are actually compliant with the requirements of the standards. And that's conclude the webinar. And thank you very much for your time and attention. We can move on to the Q&A session now.
Thank you very much, Van. That was a very interesting and quite a popular topic. Got quite a lot of questions here for you, so if you're ready, if you want to make yourself comfortable. Okay, so the first question we've got is from Tim Coffey, and he's asking, would software failures that occur because of random timing interactions be considered as systematic or random? While they may need to be fixed through a software change, they can appear to be random, and in some situations could be down to random variations in the speed of processes, sensors, etc.
Yeah, okay, yeah, that's a very good question. There are, in the literature and studies, debate on software failure, whether it's random or systematic. Software failure, and by nature, they are systematic. You can always, if you can recreate the conditions for that failure, you can always trace it back. It's to do with the implementation failure. Of course, in the complex systems, we could have, hardware failures, underlying hardware failures leading to the software failure. Again, it's systematic. It may not to do with software itself. For example, software may fail because the system resource is depleted, often not related to the, the software you're implementing, maybe to do with the systematic software. And what you're talking about, yeah, in a complex environment where there are lots of components interacting with each other, yes, the timing error, they may attribute to the processor, as is rightly identified, processor or sensor failures, issues with those, the running speed or racing conditions. And then manifest as the software failure. But if you are going back to the root cause to identify, what was the actual cause to that failure, if it is a software specific, it would have to be traced back. It will have to be systematic. You have to go back to change part of the software to address that, to make sure that it won't occur again.
Thank you. The next question we have is from Joanne Wood. How do you view the rail-specific EN 50128 versus 61508? There seems some significant differences, especially with combination of SIL.
Yeah, I mean, in terms of the SIL concept, they also use SIL concept. I actually, as I said, as part of the consultancy, we provide FSA independent safety assessment on a rail project according to EN 50128. Reading the content of those 50128 and part 3 of 61508 from a software perspective, they have a huge overlap. All the requirements, they have the similar safety life cycle for software design development, similar set of techniques and measures being published in those standards, for different stages from requirement specification to high-level architectural design, detailed design, coding, and implementation. So I actually see those two standards, EN 50128, 61508 part 3, they're very much aligned with each other from a software perspective. There are differences, obviously, because historically they developed, for example, similar to rail industry and also nuclear industry, those standards and IEC 61508, they were developed in similar timeline So there are some deviations, some differences, but I don't actually see there are significant differences, especially from a software perspective.
Thank you. The next question we have is from Stephen Hughes. EM 50128 scope is for communication, signaling and processing systems, software for rail control and protection systems. This is not appropriate for smaller safety critical systems. How do you justify using an appropriate software safety standard which may be different to the domain standard?
Yeah, on that question, and again, I might have different opinion from than yours. And the basic functional safety standard 61508, it's fairly generic. You know, they're using generic terms as well. They're not trying to, you know, say this 61508 should only be applied to a smaller system rather than a large system. The core concept, the fundamental concepts implemented in 61508, a sort of common to all different software systems. Of course, if you go to IEC 61511 on process sector specific standards, yeah, that is it's an end user standards. The focus on application program. We recall we talked about system software and application software. The application software, they using, you know, their logic often very simple. This safety instrumented function, they're simple ESDs, emergency shutdown systems, simple logics. The application logic is fairly simple. Therefore, when you implement them using ladder logic or other type of limited variability languages, you would say that's different from what we're dealing with. We're dealing with a very complex system. But 61508 for device manufacturers, for example, PLC manufacturers, they are engineering systematic system software. Like an operating system for PLC, they are complex, you know, so it's not limited to just applying a small system. As I also answered in the previous question, 50128 and 61508, they have a lot, I would say they have more similarities than differences from a software perspective.
Thank you. The next, I think we've only got time for a couple more questions. The next question is from Andrew North. Many complex systems include the use of COTS items. 61508.3 doesn't deal with COTS. Route 3S non-compliant development would seem to be the closest route, but requires a software safety requirement spec and especially design info, which isn't usually available for shrink-wrapped COTS. Is consideration of COTS going to be included in the 61508 update? Thanks.
A simple answer is it's already provided, you know, provisions are already provided in the existing 61508 standards. There will be updates on that respect. It's actually not routes. Well, 3S is one of them. There are 2S as well. 2S is the proving use. So proving use route basically says a piece of software has been proven use in the wider market. If you can gather very good, robust data, failure data associated with it, you can justify it to use in a safety-related system. So route 2S, proven use, can be used. Route 3S is non-compliant development, yes. So both routes can be used. There will be significant effort involved in actually using those two rules because retrospective assessment, also the standards require you have adequate documentation, adequate V&V to support it. And also on the issue of data gathering is currently lacking in the industry. So if you have adequate, very robust data gathering recording system, Route 2S and 3S can be used. In the next edition of the 61508, Route 2S will be significantly expanded, precisely for the reason, for the example given in the RNE 5 accidents, where you reuse a previously successful software that caused a catastrophic accident. So from a software perspective, going through Route 2S, you will still have a lot of effort, a lot of hoop to go through. But for any new projects, any new system, you should really go with compliant development route, which is route 1S.
Okay, and just one last question for you. This is from Paul Ricks. Thank you for the presentation, Fanny. You very quickly mentioned cybersecurity early in your talk. How do you see this impacting the current safety standards in the near future?
Yeah, that's again a good question, and very hot one at the moment. From a software perspective, cybersecurity will always be with us, and you see day in day out from the newspapers, there are cybersecurity accidents or incidents that actually affecting our critical infrastructures. Just earlier in this year, we have a water plant, an attacker trying to poison a water plant. Another one was the Colonial Pipeline ransomware attack that shut down that industry processes for several days. It is very important. There are separate standards, so cybersecurity standards. The one that is most relevant to the OT cybersecurity is 62443 at the moment. So that's the cybersecurity standards for industry automation and control system. The new functional safety standards, they all have a mentioning of cybersecurity standards. However, the standards themselves won't be able to cover those because they are quite distinct domains. So in 61511, they have a specific clause saying you have to perform cybersecurity risk assessment and implement countermeasures to address the findings, but then cross-reference out to standards such as 62443. In the next edition of the 61508 standards, again, similar approach will be taken. So we would have a guidance that you have to consider security risk, but the security risk will not be covered by 61508. You have to go to the domain-specific cybersecurity standards, for example, 62443, to address those aspects. Okay.
Thank you very much. Right. Any questions that haven't been answered this afternoon, Fan, you'll be answering them in writing?
Yeah, that's correct.
Okay, well, thank you very much, Fan, for a very informative and very interesting presentation. It's thoroughly enjoyable, and some very good questions from our community. I'd like to thank first of all, I'd like to thank Fan for giving this presentation, and I'd like to thank Colin for arranging all of this and making this possible. Right, so the next thing is how to access the webinar recordings. Now, all webinar recordings are archived under the Resources tab on the SaRS website. SaRS members can access this archive as a member facility. You can join as a full member or the simplified associate of the society grade, which gives you access to all the SaRS resources, including the webinars. Just go to www.sars.org.uk. This webinar recording will be available in a couple of days, so keep an eye out if you want to see it again. Okay, for joining SaRS, if you aren't a member and have enjoyed this webinar, please take a look at our website, see the benefits of membership and join us. Safety and Reliability Society is the licensed member of the Engineering Council for CEng and IEng professional registration. We accept membership applications from candidates from all relevant backgrounds. Membership is open to everyone from students to experienced professionals. More information is available at the SaRS website. And just to give you a bit of an idea of the upcoming webinars in the 2021 programme, we've got the fifth and final part of the Technical Learning webinar series on functional safety. This will be presented on the 18th of August 2021 at 1 p.m. UK time. It will be presented by Paulo Oliveira of Engineering Safety Consultants Limited. There will also be a presentation on the 15th of September at 1500 hours Hong Kong time by the Asia Pacific branch, and that will be presenting the rail tunnel safety. This will be presented by Dr. Fatih Tarada of Mosen Limited. And then on the 22nd of September 2021, the London branch will be presenting its annual Early Careers presentation. The event will take place at 6 p.m. UK time. If you would like the opportunity to present and you have less than 10 years of experience in the safety and reliability sector, interested in presenting to this live webinar event, please send a short abstract, approximately 250 words, on the proposed topic and a copy of your CV to Colin Dennis at londonbranch@sars.org.uk by Friday the 13th of August. Okay. I'm now going to initiate a feedback form. Again, thank you everyone for attending. Please can I ask you to fill it in before you exit the webinar? The information is vital for us to improve our offering. Please take 2 minutes to fill it in and click submit. Your CPD certificate will be sent to you if you requested one at registration. Thank you very much and stay safe.